So I'm going to cover the how, the what, and the why of the CMB. So, how was it discovered? What is it? And why is it useful? In order to do this, I'm going to cover a little bit of background first. Probably most of you will know it, some of you won't, so I'm going to cover it anyway because it's always good to remind you. So, an electromagnetic spectrum. Basically, this is just waves. So here is the light that you see. So this is the light spectrum, and then this is gamma rays. These are really high energy. These are the radio waves that you hear on your radio, and this is microwave here. So that sits between this radio waves and these visible light rays. So the microwave part of this spectrum is what we're going to be talking about. And these waves of electromagnetic energy, we call them photons. Right? I'm going to mention photons. That's what a photon is. Right. So for our story, we have to go back to the 1940s, which you've already kind of heard about in the reading before. So lots of people made predictions about a temperature that would be measured in the universe, but it was actually Alpha and Herman who said that it didn't matter where you were in space, you would always measure the same temperature. So they said that there was going to be this universal temperature out there, and they said it would be roughly about 5 Kelvin. So then about 15, 20 years later, this telescope was built in the Bell Laboratories, a radio telescope, and Penzias and Wilson were the operators of this telescope. So it was built just to do some radio astronomy experiments and also to do some satellite communications experiments. So they built it, they set it up, they started taking data, and they noticed that in their data there was always this excess of 3 Kelvin. So that's 3 degrees above absolute zero. And they were like, well, what's this? This is a bit weird. So they tried to get rid of all the sources of error from their data. They did everything they could think of, and they even went as far as climbing up onto the telescope and scraping pigeon poop off it, because they thought that maybe that was introducing some background noise. But actually, it wasn't that. It was still there. They couldn't get rid of it. So what they were seeing was something a little bit like this. This is actually not the original picture, because due to the government shutdown in America, you can't access the so this is a very rough estimation of what they would have seen, and it's basically the same. So they just saw this wash, and it was particularly strong in, yes.
Is this a paint estimation?
No. This is an actual picture. Okay. It's not the picture from the Bell Labs, but it is a real picture. Okay. I didn't just sit and paint and do it. Yes, so this radiation was particularly strong in the microwave area. And so they just saw this wash across the whole sky of radiation. And it was so strong in the microwave band that it was even obscuring their view of the galaxy. So this little blue band here that you can see is our galaxy, is the Milky Way. And actually, that should have been really, really strong and really bright, because we're in it, right? So it's really close by. But actually, this background radiation was so strong it was even obscuring their view of the galaxy. So they didn't know what it was at first. They had to think about it. They called up some scientists, and they came to the conclusion that actually this was the cosmic microwave background, the CMB, that Alpha and Herman had predicted. And indeed, as you heard, in 1978 they won the Nobel Prize for this discovery because it was huge. Right, so that's all very well and good. They discovered it, but how did it get there in the first place? Where did it actually come from? So for this, oh actually no, I'm not going to talk about that. So they found the CMB, and then scientists were like, right, so we found this CMB, we want to know a bit more about it. Is it really universal across the whole sky, or is there some more detail there that we can find? And so they sent up various experiments. There were some ground-based experiments, and there were also some balloon experiments that they sent up to try and take measurements. And then as our technology got better, they sent up satellites. So the first of those satellites was COBE, so that's a Cosmic Background Explorer. That went up in the early 90s, and I'm going to come back to that slightly later. Then WMAP went up in 2001. That took data for 9 years. And then Planck was the most recent one. You might have heard about it in the news. That went up a few years ago, and it's just sent back some of its data now that's being analysed. And this is a little infographic, and you can see how much our technology has advanced over the years. and the improved resolution that we're getting. Because at first we had that green wash, didn't look like very much. Then Kobe, already you can see a bit of difference, a bit of resolution. Then WMAP saw this, and then this is what Planck sent back. So this is an incredible improvement in resolution. Let's just appreciate that. I mean, these telescope builders did a pretty good job. And so then we got this, the very final result. So this is from Planck, because Planck is ESA, so that's European Space Agency, so I can still access their data. And so this is the image that Planck sent back. So actually, that's a folded out sphere. So basically that is this, a sphere. So really what you need to do is you need to picture that this is actually on the inside, and we're also sitting on the inside of this and looking out at this radiation all around us. You might be able to notice that there's a key difference between this and that's this red band that's going all the way around it. Well, that is because that's our galaxy, so that's the Milky Way. And so when we're looking out, because we're sitting in the galaxy, we can also see our galaxy there. And so this is the radiation that's given off from the galaxy. Yes?
Sophie, so in order to get this CMB picture on the screen, you have to subtract?
You have to subtract the galaxy, yes. There's also a lot of other noise that goes on, and they do some very clever physics to get rid of all the backgrounds.
Is it like a very accurate subtraction?
It's pretty accurate, yeah. I mean, there's a hell of a lot that goes into it, and they really know what they're doing. Yes?
I'm sorry, but you told that it should be like uniform somehow in the whole universe.
Hold on to your question. Hold on. We will come to that. That is very interesting.
And my other question is, how can you like subtract the thing? So you cannot like go out and see it from different perspectives. So how do you know that something comes from a galaxy and something comes from this background radiation?
So a lot of that comes from our understanding of the astrophysics around us. So we understand galaxies, we understand the radiation that they give off. This is also actually, this red bit is really obvious as well. Like, we know that we're sitting in the plane of the galaxy.
Oh, okay, because it's like a temperature picture that you see here, and here you see like what you see, it's like a whole spectrum, and then you can identify that
exactly,
it doesn't look like something.
And there's lots of other bits of noise that come from,
okay.
And it's a lot of astrophysics that goes into it that they know about, and also some other stuff. But not being an experimentalist, I don't know the nitty-gritty of how they do these extractions.
It's also the fact that Planck doesn't just measure one frequency, right?
Yeah.
Measure different frequency of the
and then you see this spectrum, and you can say, oh, it looks like a spectrum of a star, not a spectrum.
Exactly, the CMB and the galaxy have different spectra, so you can.
Yeah. I didn't put up all the different spectrum pictures because we were doing it all day. Right. Yes. So CMB. Great. So then, how did the CMB actually get here? This is the bit that I tried to get to earlier. So, for this, you have to go to the very beginning of time, the Big Bang, when the universe was created. So, from a point, it expanded really fast. It was really, really hot. It was a very unpleasant place. Everything was ionized. That means there was loads of electrons flying around, loads of protons flying around, and photons couldn't travel anywhere because the photons were always interacting with this charged matter. They couldn't get anywhere. And then as the universe continued to expand, it cooled down. And then the electrons and the protons were able to form neutral atoms. Neutral hydrogen, mostly, is what they started out forming. And so then, the photons were able to travel through the universe. They were free-streaming, you say, so they were able to just travel through. And so, at the transition point here, is when the CMB was created. So, the CMB is the imprint that was left when the universe transitioned from being opaque, because the photons couldn't travel, to then being transparent when the universe could travel. So that's the imprint that was left, and that's the fingerprint, so to speak, that was left, that signature of what was going on back here. And so that is actually the key thing about the CMB that's really fascinating, is that this tells us what was going on all around here as the universe was created, because all of that information feeds into this imprint that's left in the sky. It also tells us about what went on over here, because the cosmic microwave background was formed 400,000 years after the Big Bang. So that's really early on. When you think that our universe is 14 billion years old, nearly 14 billion years old, 400,000 years, that's basically the beginning of the universe. And so it's got a very, very long time to travel before it gets to us. So it's going through all of this bit, all the star formation, all the galaxy formation, everything in the universe is forming, all the structures and stuff, and it comes through all here until it reaches us in Earth or our satellite. So, that's all very well and good. But in this assumption, I've said to you, there was a Big Bang. Is there really a Big Bang? There was a Big Bang, because the CMB gives us a really big piece of evidence in support of the Big Bang. And this is one of the most exciting things about it. So, this is to do a little bit of physics. So, the Big Bang theory predicts that the CMB should be a black body. Now, a black body is just a perfect radiator. So it tells us that there is a very distinct pattern that an object will emit its radiation in. So how its radiation, the intensity of the radiation that it emits, will vary with the frequency or with the wavelength, however you want to think of it. So, for example, the sun is a black body. And this green curve here is the shape that the radiation of a black body should follow. So for the sun, if we measure the radiation coming from the sun, we'll see this green curve, and the peak of this green curve will correspond to the temperature of the sun. And so, if we draw this green curve now has actually been drawn for the CMB, and this peak of the curve corresponds to the temperature of the CMB. And now this green curve is a theoretical prediction. That is us saying, well, the Big Bang predicts that the CMB should be a black body and it should emit radiation in this pattern. And so, let's draw a green line showing what we think it should look like. Then, COBE went up, the satellite that I mentioned before. It took lots of data, and then the data that COBE took are these red points here. And as you can see, now this is incredible, the data matches absolutely perfectly with our theoretical predictions. In fact, the error bars on those red points have been exaggerated so that you can actually see that there are error bars. So it's even more perfect than it looks. That's incredible, right? We had a theory, we made a prediction, we took some measurements, and they match up perfectly. And so the steady state theory, that was the more favoured model at the time, which says that the universe is infinite, it has no beginning and it has no end, is completely thrown out the window, because that theory does not predict that you will have a spectrum like this. And so, the COBE team won a Nobel Prize in 2006 for this, because that's amazing. Right. So, then we come back to this, and the fact that it doesn't look very uniform. Well, so these blue bits are the coldest bits, and the red bits are the hottest bits. So you can say, actually, it doesn't look very uniform after all. It's all a bit different, and everything's different, and it's not all a uniform temperature. Aha. Actually, we're highlighting very, very small differences in temperature here. So actually, overall, these differences are 1 part in 100,000. So that's tiny. So we're highlighting the tiniest of changes. So actually, the universe is a universal temperature. And that means that actually the universe is homogeneous and isotropic. So what does that mean? It means if I go out to a point in space and I look in every direction, then on large scales, everything I see is going to be the same. And if I go to another point in space and I look in every direction, then on large scales, everything is going to be the same as what I just saw before. Now this is fundamental to our understanding of the universe. So much so that the fact that the universe is homogeneous and isotropic is called the cosmological principle. And that feeds into a lot of theories of cosmology. It's what a lot of things are based upon. Also, an interesting point to note here is that even though these differences are absolutely tiny, these small fluctuations are what seeded structure. So So if those fluctuations weren't there, if this truly was completely uniform, like that green smear that I showed you before, nothing would have formed. There would be no stars, no galaxies, no dark matter, no nothing, and we wouldn't be here. So it was just these tiny, tiny, tiny little variations that means that everything can form. So that's pretty cool, pretty interesting. Finally, we've got this one. This is a little bit more complicated, but you don't need to worry about what the axes are telling you. Basically, this is a measure of like objects on the sky. So this is big objects, this is small objects. So if we just have a look back at our CMB here, so you've got these tiny little things here, and these big kind of structures here, basically. And this is just a measure of how much power is contained in the small ones and how much power is contained in the big ones. That's essentially all you need to know. So, again, our green line is a theoretical prediction. So, one of the most favoured model of cosmology is the lambda CDM model. So the lambda CDM model says that the universe is made up of three things. It's made up of dark energy, dark matter, and baryons. And baryons is the matter that you see around you, that you're interacting with. So, if we say that the matter is made up of these, if the universe is made up of these three components, then we can make our theoretical prediction of what this kind of graph would look like, and we draw this green line. A theoretical prediction, green line. Planck went up, it took lots of measurements, and it sent its data back. And then Planck is all these red dots here. This is beautiful, absolutely beautiful. I mean, art is beautiful, but this is beautiful. I mean, this is incredible. Our data matches perfectly with our theoretical predictions. I can talk about that one afterwards if you want, but let's just look at this bit here. Look at it, it's amazing, right? We came up with a theory. We said the universe is made of these three things. We made a prediction, we measured it, and it matches. That's amazing. So there you go, right? That's pretty cool. So that, the CMB is pretty important. Like, that tells us a lot about the universe. Also, not only is this telling us what the universe is made up of, it's also telling us how much there is of everything. So from this plot, I can tell you that there's 70% of the universe is made up of dark energy, 25% of it is made up of dark matter, and about 5%, the remaining 5%, is made up of baryons. I can also tell you how fast the universe is expanding, and various other cosmological parameters. This is a wealth of information, and that is really one of the most important things about the CMB. Because previously, cosmology was just people sitting in rooms, making predictions, building models, and saying, the universe is like this, you're just going to have to trust me, because how are you ever going to be able to measure the universe? Well, we can measure it now, and this is it. It took cosmology from the theoretical into something that can actually make solid predictions that can be tested and verified. Wow. Okay. So,
Sophie, can you talk a little bit about that ugly tail?
yeah, so this bit, this is not our fault. So this basically not our fault, really. So that comes, it's something called cosmic variance. And so that's to do with the fact that we only have one universe to measure. So this, as I said, is the largest objects on the sky. So when you're measuring really big things, then there's not going to be very many of them, and you've only got one universe in which to measure it. And so that gives you quite a big error bar,
But
because
it's
you can't
infinite,
compare.
come on.
Sorry? Oh yes, it's infinite. But we can't see that. We can only see
Yeah,
up
we are
until-
in one point of view.
Yeah. So that's where those error bars come from. So that's not to do with the inadequacies of our equipment. That's to do with the fact that we only have one universe to
But the
measure.
error bars will be decreased with better telescopes. I mean, is it
On these
the case?
ones, no.
or-
So actually, I don't know whether you can see. You see this green shaded region.
Yeah.
Can you see that at all? So this is what comes from cosmic variance. So
Uh-huh.
this you can't narrow down anymore.
Okay.
Because there's only one universe, and that won't change.
And what about that little dot there whose error bar is outside the cosmic variance?
This one.
Like every other point I'm fine with, right?
This is actually quite funny. So, a lot of people have jumped on this actually, and they're like, oh my god, lambda CDM, it's not true. Look at this point. And people have come up with various explanations for it, and blah 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 and whatever. But I
There was
think
poop
it's
on
just
the
a measurement
telescope.
thing, really. Like, yeah, I think that really, if we have another satellite that goes up and takes more accurate measurements, in my opinion, I don't know what Mattia would say, but I think that this point is going to move uphill. Really, I think that's a measurement.
I also think that, but
would you agree with me? Yeah.
maybe that's just because we're theorists, so we think, oh, the experiment measures wrong.
So I have a question about these temperature fluctuations. What is the reason for these fluctuations? Is it so that it was like it's not really equilibrium and
so that was that goes back to right at the beginning of the universe, and so there were quantum fluctuations, so very small, sort of like little kind of particles, I suppose you could call it, at the very beginning, and those fluctuations are then seeded the fluctuations in the whole temperature. I can talk about that afterwards, but it's probably not a good thing to talk about with everybody. Right, so theory, data, matches, great. So to end on a fun fact, if you detune your analog TV, you get static like this. So the CMB is so strong in the sub-millimeter region, in those microwave regions, that actually, when you look at this static, a few percent of that comes from the CMB itself. So actually, if you're looking at static, you're looking at radiation that came from the very beginning of the universe. It's pretty cool.
Wow.
Good job. Do we have more questions for Sophie?
Don't involve quantum fluctuations.
Or how our TV works.
Yeah.
So if we send an even better satellite, are we going to see more details in the radiation?
Mm-hmm.
So we'll be.
Yeah, it'll be even better. So if we go all the way.
So is there an actual limit to those, to the size of those fluctuations, or not?
So there's a limit to how good our resolution can be.
But the actual radiation. I mean,
I wouldn't say so, because, well, the thing is, it's hard to know, right? Because when we sent up Proby, we thought that this is all we would see. And then we sent WMAP up and we got even better resolution. And then we sent up Planck and we got even better resolution.
You mean that there would be a possibility that on top of that fluctuation there would be even smaller and smaller?
Yeah,
and
would
that
we
would be
see
amazing.
more? Yeah,
Well, there's
we
also
don't know.
polarization, that apart from the scalar fluctuations, in the future we'll be able to measure tensor perturbations and gravitational waves. And,
Yeah.
and
So, I mean, there's a lot more
stuff
to measure, yeah, like Dimitri said. But as for how good, I mean, we don't know how
so
good the
that is
resolution
coming
could
from
be.
the quantum fluctuations.
Yeah, from the very beginning of the universe.
So they're kind of imprinted now in.
Yeah, basically. And so those tiny little fluctuations seeded structure, because then you've got like dark matter that would start to clump around these like kind of little imperfections, a bit like in a water glass. If you have, like, you can't get bubbles forming unless you have like some sort of like imperfections in the glass on the inside. It's kind of like that, really. That was really good. Leaving that one.
Somebody
Leaving that.
And everybody will go home and switch that.
My enthusiasm has stunned everyone. Yeah, false anything on the backside. I got really enthusiastic.
Okay, well, thanks again.
Yeah.
So see you tomorrow. You start again at 7 and tell your friends you want more people. Tomorrow we have 2 talks again and 1